Welcome everyone to CSE 291D 234 Data Systems for Machine Learning. My name is Arun Kumar. Continuing our invited industry guest lecture series, today we have Dr. Angela Jiang from Determined AI. Angela has been working for years as part of her PhD on deep learning systems. And so it's really a pleasure to have her join this class and tell our students and others about systems problems in deep learning. So protocol for the talk. This whole thing is being recorded and will be posted publicly afterwards. If you have any questions, feel free to raise your hand. Angela, do you prefer questions during the talk with interruptions or all at the end?
Yeah, interruptions are great.
Okay, wonderful. So students, please raise your hand on the Zoom participants list and I will pause at an opportune time for her to answer. And if she also might prompt for questions. So at that point also you can answer. And if you want to put questions in the chat, that's fine too. Okay, with that, we'll hand it over to Angela. Take it away. Thank you for joining us.
Awesome. Thank you guys so much for having me. So like I mentioned, I've been working on ML systems both during my PhD and now at Determined AI. During my PhD, like I mentioned, I was at CMU working with Greg Ganger and Dave Anderson on machine learning systems. And now with my time at Determined, I'm a product manager, and at Determined, we work on essentially infrastructure for deep learning training. So a lot of similar problems as in my PhD. And I would say during that whole period of time, I realized, how much novel systems work there still is to be done to power advances in deep learning. And today I'm going to be talking about a lot of those problems and really why I think, deep learning is just as much a systems problem as it is a machine learning problem. Okay, so like all of you guys, I'm sure, are aware of, advances in deep learning have enabled some really cool applications like autonomous vehicles, medical imaging systems, translation systems. And as a field, it's really showing a lot of promise. But while a lot of people might think of advances in deep learning as mostly advances in model architectures or new ways of doing non-convex optimization, new data sets, really just as much, it's been powered by underlying advances in the software and infrastructure that's powering these deep learning algorithms. Famously, neural networks have been around since the 80s. So you can argue that really what caused the proliferation of deep learning is the ability to run backpropagation on an accelerator or to scale out training to so many machines that you can now train on data sets of millions of examples. And the reason why, we need these kind of advances in software and infrastructure to power deep learning is because deep learning is just fundamentally different than the kinds of software engineering that we used to have. So we no longer can rely on old ways of running systems and providing infrastructure support. Because if you think about, what it takes for a software engineer before to write the applications that they wanted to write, a couple of assumptions hold true. You don't expect to be working with a lot of data. You can get away with just using several cores of CPUs. So you can basically do all of your debugging and engineering on your laptop. And even just running on your laptop, compilation and iteration still takes just seconds. So you have a very fast iteration cycle, and you also have a very well-defined understanding of what correctness means in this world, and likewise how to debug for it. But then if you consider deep learning engineering, none of these assumptions end up holding true. Now we could be working with, tens of terabytes of data. There's really no amount of compute that really feels like enough. And so you want like teraflops and petaflops. And so you ultimately need to rely on having accelerators, GPUs, or even TPUs to be doing your training. And even with lots of accelerators, lots of computes, the actual iteration time of getting a signal for like something like training and even inference can be days and even weeks if you're not careful. And so now you have a much longer iteration cycle. And not only that, but it becomes very difficult to reason about correctness in this world because everything is very probabilistic. And likewise, again, it's very difficult then to be doing debugging. And so if you're interested in systems, which I can imagine a lot of people in this class are, And this is great news because there's a lot of really interesting problems to be tackling. So in addition to, the typical machine learning and systems conferences in academia, there's of course conferences and workshops dedicated to machine learning systems in and of itself. And there's many, many startups that are proliferating with the sole goal of making the ML engineer's life easier by providing systems and infrastructure support. But if you're interested in just doing machine learning, then the status is a little bit more bleak, because as a machine learning engineer, you would hope that you really just get to live using PyTorch and Keras and thinking really about machine learning problems, like what model you want to use, what optimizer you want to use, what data set you want to train on. But really, when you're doing machine learning engineering, as many of you guys probably know, you actually have to be tackling a host of systems and infrastructure machinery just to run the things that you want to run. And so, at least in my graduate program, and even now, the tooling and the infrastructure support wasn't there. So this is essentially where I lived in grad school. When I wanted to do machine learning, I basically was spending time writing out that software infrastructure code, that boilerplate code, just to get things running at a state where I could actually iterate on some machine learning. So this was not ideal. It didn't feel right at the time. It felt like this was a very inefficient way of iterating on machine learning. And I was used to regular software engineering, so it just felt like the ML or the actual workflow itself was very immature. And that ended up being right, because at this point, we don't want machine learning engineer to be having to focus on any of these infrastructure tools, really. And that's what the people in both industry and academia have realized is one of the most important problems if we're going to continue making advances in deep learning. So when I got to determine, what I realized by talking to other PhD grads there is that essentially we were all living the same life. We were all trying to do machine learning for different reasons and different projects, but we just kept running into the same infrastructure problems over and over and over again. And those would be problems like figuring out how to distribute training, figuring out how to track experiments, run hyperparameter optimization, manage our infrastructure. And not only did we have to, run or write this code and manage this infrastructure on our own, but we had to do it essentially every time we needed to spin up a new project. So for instance, for infrastructure management, what we did in grad school was extremely ad hoc, because for one, the first thing you have to do in grad school is you just have to find accelerators to work on, which can be very, very difficult. We had essentially, one cluster or a cluster for each different lab that was run by different professors. We also had our individual machines. For instance, this is me being very excited getting my Titan V, setting it up, and then ultimately sharing it with my friends. We had machines that people would just forget about over the years. And then when we were really desperate, we would be like, do we know any machine with a GPU in it? And we would dig up these machines that hadn't been used. Or in very, very desperate times, this picture I've included is actually a picture of my advisor's data center that he built in his garage. We call it Garage Center, which had 12 Titan X's in it. And that when we really came to crunch time, you get to use the Garage Center and run all your experiments really quickly and essentially heat up his garage like crazy. But you would go through this whole process of finding machines at the right time, and every machine required management. You had to figure out, if and how to connect up your GPUs. You needed to figure out how fast those GPUs were, how much memory did they have. If there were other people running on the machines, you might not be able to run because if someone's doing performance benchmarking, you can't be sharing this infrastructure. You might even run out of memory. And once you actually had these machines up and running with the hardware that you wanted, you also had to manage what experiments went where. Because with 7 different types of machines around and 20 different experiments to run, now you basically have to be a manual scheduler to be like, I'm going to run this experiment on this machine and remember that and make sure that output doesn't clobber another output. It was very, very manual and certainly not ideal. So once you actually manage to start running your experiments on these different machines, ultimately you have to make sure that you save the results in a way where you can not only know what happened during the training experiments or during the experiments themselves, but also in a way that you could share your results, that you could reproduce the results, and that you could also allow other community members to reproduce your results on their own experiments or on their own setups. And so again, we approach this in an extremely ad hoc way. We, for the most part, just relied on our file systems. We would essentially have tens of gigs of files there of model checkpoints, training codes, scripts, PDFs of different graphs. And it was pretty good that at some point I thought to upload all of this to Git. And that was essentially the experiment tracking and reproducibility story. And so I just pulled, what one of my GitHub repos looks like. And here I have, the nice directory structure where I have things that are pre-2018 spring and 2018 spring in different directories. So clearly I uploaded all this stuff in 2018 of spring. And I also have, extremely long, well thought out file names like output/streamer/schedule/atc 05031, which was probably the date that I had created that file. And this was essentially how we tracked the results of all of our long-running experiments and would go back and try to reproduce these or showcase the results. It was very, very messy, like I said. And then it would come a time where, we would have to distribute training for a variety of reasons. Like even when I was doing grad school, doing distributed training was pretty much table stakes. And I would argue that now it's even more important to be able to scale your training with the advent of new NLP models just to get state-of-the-art results. But for us, oftentimes we would have to retrain image networks from scratch, or we would have to make sure that we could run a bunch of experiments, within a week so that we could meet a paper deadline. And so distributed training was pretty early on something that we all had to figure out. And at the time, it was just, when I was getting started with distributed training, that TensorFlow actually open sourced their version of distributed training to use. And I think that I never actually got TensorFlow distributed training to work. I think instead what I did was I just parallelized my experiments as opposed to parallelizing a single experiment, which is definitely not ideal. I just didn't have the patience for it at the time, I think. And I also pulled up this email thread that I remember having where I was at Google Brain working on something about TensorFlow. And I was sitting next to the team that was working on distributed TensorFlow. And I knew that, my teammates and my lab mates were struggling with this kind of thing. And so I remember soliciting, questions from them when I had 2 weeks left at Google Brain to be like, okay, what are your questions? Let's try to get all of our questions about distributed training out now while we have access to these people. And I remember running around Google Brain trying to make sense of these things. And fortunately, it's a lot better now, which I'll talk about later on in this talk. But this is the kind of stuff that we went through just to try to get, the baseline distributed training running in the early days. And finally, again, at some point in our workflow, we would run into having to do hyperparameter optimization, which just really, really stress tested any of our workflows. Because now, instead of trying to run one long-running experiment and finding GPUs for it, we now need to be running 100 of those experiments and getting a signal from it. And so what I did here was essentially I, just figured out what my search space was and then did an ad hoc grid search where I found different points in space and figured out, okay, well, I can run 7 of these at a time, and let's just queue up all these experiments and get a reasonable sense of the space. And that worked, for a while. But ultimately, something like hyperparameter search actually made it into, one of the core algorithms that I needed to run for my research. And so that kind of thing didn't fly anymore. But fortunately, at that point, it was my last year in grad school, which meant my workflow, was cobbled together enough that I did have distributed training. I did have some version of experiment management. So I was able to inject also, a more sophisticated hyperparameter search mechanism to run this. But for most of my grad school program, I didn't. I just ran a grid search. So this is all to say that, again, as someone that's trying to just do machine learning engineering, there's just all this other stuff that you end up having to do that just has nothing to do with the actual machine learning that you want to run. And this is not actually how we want the experience of an ML engineer to go. And so today I'll talk about, the software support that we have created for each of these different infrastructure problems, as well as some existing problems that are still around today that we continue to try to solve both in academia and in industry. So actually I'll stop there and check if there's any questions so far.
Okay, thanks, Angela. Questions from the audience at this point? If not, let's continue. I do have some questions, Angela, but probably let's get further into the talk and then I can ask them.
Okay, sure, sounds good. Okay, well then in that case, we'll move on to distributed training. So I think you guys have talked about distributed training in this class before. There's two kind of typical algorithms that you typically hear about, either data parallel or model parallelism. And in industry and in practice, most people are running data parallelism. So I wanted to run through, just how data parallelism has evolved, over the last 6 or so years in the state that it's in now, because it's improved quite a bit. So the general premise of data parallelism, just so we're on the same page, is that we have a model and we want to train it using multiple GPUs or multiple machines. And so what we're going to do is we're going to have a copy of the model on every machine or every GPU. And then we'll train these copies essentially in parallel with different subsets of the data. So when you're training with a different subset of data, of course, what you would expect is you to have every machine come up with different gradients that we want to then apply to all of the models. And so with two machines, it's pretty simple. Every time you have a gradient update, you push it to the other machine so that they can also apply the same gradient update. And in that way, your model is always in sync and you get one final model in the end. So in 2014, we really had the first paper that came up with essentially a very principled way of doing this communication, especially as you start scaling. So that was the parameter server. It came out by people from Carnegie Mellon, as well as some other places. And this was really the de facto way of doing communication for distributed training for the next couple of years. In fact, I think it was already what Disbelief was running within Google. But in 2016, TensorFlow then actually released a version of the parameter server into TensorFlow open source so that people could actually use it. And this is the kind of stuff that I was struggling with Aaron in that email train. But it was a way of people in the open source community to actually be running distributed training with TensorFlow. So I just wanted to go through the general principles of the parameter server, but in particular focusing on the kind of systems optimization that they came up with. So with a parameter server, what we had was essentially centralized communication of all your weights. So instead of some sort of all-to-all communication between your different machines, you had one central server that would have one ground truth of what the weights were. So now communication is pretty conceptually simple. Every time a machine has a gradient update to push, it can push it to the server. The server could then apply those gradient updates. And so then machines can also pull a new set of those weights to make sure that they are running on an up-to-date version of the model. So in the paper, they really just had two main optimization approaches to make sure that we could deal with the amount of communication that we expect from machine learning training. And one of the biggest issues with creating this parameter server is that typically what you'd expect is to run this parameter server as a key value store. And so every key points to a set of weights, for instance, or a weight rather. And if you just implement this naively with any key value store, what you get is way too much communication overhead because the actual updates in the values themselves are very small. So they're just, floats or integers. And so one of the big things that they propose in the parameter server architecture is to make everything range-based, essentially. So essentially to batch up your updates and batch up your values. So what you have there then is that for every message going back and forth between the server and the machines, you have range-based updates. So you have a range-based push and a range-based pull, where instead of getting one key value pair, you get a full range of them. In addition, instead of having one vector timestamp per key value, you have one vector timestamp for a set of key values. So batch communication was the way to make this communication pattern actually feasible. In addition, they offered the ability to have relaxed consistency in your system. Because you can imagine that with so many machines trying to update one value of one set of model weights, that if you had to block on every update, this would end up being really slow. On the other hand, if you allowed these different machines to run on out-of-date states of the model, this could also screw up your conversion so that you don't converge as quickly. So what you really want to do is just be able to trade off that algorithm conversion rates with your system efficiency. So what they allow is for any of these tasks to be executed both asynchronously or synchronously. In this case, we run iteration 10 and 11 in parallel, but we block on iteration 12. And the paper itself, I don't think actually prescribes any consistency model in particular, but they just allow this trade-off. And there's been a ton of papers on after this to talk about really how much consistency or relaxation do we actually want. Okay, so like I said, the parameter server really took off. It was the basic way of doing communication for a long time. And then in 2016, TensorFlow releases their version of parameter server. But what we find is that while this works pretty well, there's still a communication systems challenge, because this is, at the end of the day, a centralized communication method. And so there's a bottleneck at the server. So you can imagine, as you have more machines, all these machines are trying to talk to the same exact server. And so now the server is the bottleneck. So one way of getting around this is just to have more servers and to scale out the number of servers so that you could, for instance, shard the key set to every different server. So now, depending on what key you actually wanted to update, you would go to a different server. And that can help in a lot of cases. But as you get more and more servers, you end up having essentially an all-to-all communication pattern, which again can be the bottleneck. So to address this, there was, in 2018, another type of communication pattern that started getting popular, which is the ring or the allreduce pattern. And the ring and the allreduce pattern essentially is a decentralized approach, where now you don't have to talk to a centralized server, but instead you share your updates with your neighbors. And now the upside of this is that you have a lot fewer bandwidth bottlenecks in the system. And the downside is that you're a little bit more susceptible to failures. When your neighbors fail, you can't communicate with them, so the algorithm gets more complicated. But this ultimately became a very popular way of running communication pattern, especially with the introduction of software called Horovod, which I don't know if any of you guys have run Horovod before, but essentially it was software for distributed training that was released by Uber in 2018 that implemented this allreduce algorithm. And this is what they showed, is that using their algorithm and their implementation, they could get much more true scaling than TensorFlow distributed training. But not only that, but Horovod also really improved the user experience, which I think in my view is probably more important than actually providing the actual level of performance improvement, especially for independent researchers or small startups. Because with something like TensorFlow, I talked about a lot of the problems that we ran into when we were trying to get this set up, especially early on. But even towards the end, there was a lot of manual stuff that you had to do. So you had to make sure that, of course, you started all your machines, that they could communicate with each other. You had to manually start, your parameter server. You had to manually start each of the workers. You had to make sure that, you passed around all the state that allowed you to communicate with the workers and the servers, things like the IP address and the network ports. And you also had to make sure that, the training objects that you made had access to the right information at the right time using like some subset of these API calls, which I'm still exactly not sure which ones. But what Horovod did instead is that it really made this a lot easier to run from a user's perspective. So Horovod, I won't go through it all, but essentially it will run one version of the script on different machines. And it itself will set up, the communication between the different machines, and essentially also take care of the allreduce communication and the gradient updates at the end. And so what you really have to focus on is, setting up Horovod by creating, your trial script that does things for different GPUs, that knows how to sync up, your gradient updates at the end, and also tell Horovod what machine you want to run on. Which is still not ideal. It's still a lot of information to pass and stuff to set up, but it's a little bit higher level than the TensorFlow operation. So fast forward all the way to today. Now I would say, we've really gotten to a good place with distributed training. With something like Determine, you don't even really have to think about, machines running different sets of models and communicating with each other, kind of like all the stuff that basically we just talked about. But with something like Determine, now you can just think about, okay, so for this training script, I want to run on 8 machines or 12 machines and configure it in your configuration file and just let it run. And now it'll take care of stuff like making sure that there's different models on different machines, that different data is getting to the different machines, that if one of the machines goes down, that you know how to save the state so you don't have to start over, as well as restart the job somewhere else, and those kind of infrastructure issues. Okay, any questions about distributed training before I move on?
No, I think we can continue, Angela. Students have studied these systems also in this class, so they are quite familiar with some of these systems. So I hope they all followed along. So thanks for recapping some of the details.
Cool, very good. Excellent. Okay, so then we'll move on to hyperparameter optimization. So I think I'm assuming that also people have learned about, basic hyperparameter optimization tuning algorithms. Is that right, Arun?
Oh yeah, we covered hyperband and stuff, ASHA. So, but it'll be good to hear from what you're doing as well. So feel free to talk about that.
Cool. Yeah, so in this, I won't go into any of the algorithms then, but what I really want to draw out is, again, the infrastructure challenges that arise from trying to run something like hyperband or ASHA in production or at scale. Because what we've noticed is that, even though hyperband things are very popular in academia, and it's a very cool algorithm that has a lot of performance value, that in production, in our own experience, most people run things like grid and random still. And that's because we think of the large infrastructure hurdles that you have to overcome to get one of these things running. So I'll go through the kind of things that we have to do. Okay, so you guys know why hyperparameter tuning is useful. The case study that I think really draws this out from a systems perspective is something like neural architecture search, which is really taking hyperparameter search to the extreme by making essentially the architecture itself into a hyperparameter search problem, or making the architecture into a hyperparameter search problem. And the really main issue that I want to draw out here is that, for instance, in the NASNet paper, they were able to achieve state-of-the-art performance on data sets like CFAR10, but it took over 20,000 GPU hours, or I think that's like 3 months of GPU time, in order to get a state-of-the-art result on a fairly simple task of like 50,000 images. And so what that means to me is that from a systems perspective, any kind of efficiency that we can offer people running hyperparameter search or really just trying different configurations or different things when they're experimenting with deep learning is going to give you extra performance or allow you to do things you haven't done before. Okay, so what that means from an infrastructure perspective is, first and foremost, we have to manage a large set of experiments, and we have to do so as efficiently as possible. So if we're just trying to run grid search, let's say, and we have 100 experiments or so, what that means is, first and foremost, you have to be running your experiments probably in parallel. And not only that, but you have to make sure now that you have queued up the right experiments on the right machines. Maybe you want to also be managing to look for if any of these experiments have failed, if any of these experiments are particularly slow or is a straggler, you might want to actually change what work is running on that machine. And at the end of the day, when all of these experiments are done running on the different machines, there's also a lot of bookkeeping to keep track of. And so this is the kind of stuff that I mentioned having to do very manually early on in my grad school career. But essentially, you can imagine for every machine, you need to keep track of code that was run, the configuration that was run, what was the final metric of interest, whether it's accuracy or whatever. And also everything you need to debug if that would, like, why we actually got there. So including learning rate or learning curves and whatnot. Not only that, but you have to make sure that you have all of this data organized, but also accessible in a way that you can actually make sense of it. So that you can find, like the output of a particular experiment at any particular time, but also that you can visualize, this essentially very multi-dimensional set of data at once. So for instance, at Determine, we're currently working on a project to visualize the output of hyperparameter search. And what it requires is essentially looking at high dimensional data cut in maybe 20 different ways. And so an ML engineer can figure out, okay, well, I ran this hyperparameter search in a week. So what hyperparameters were actually important, what were unimportant that I should avoid next time, what ranges were good for the hyperparameters, what actually correlated with my metric of interest, things like that. Okay, so in addition, you might not want to run, just grid search. Like I said, you might want to run something like Bayesian optimization or hyperband, where what you're doing is not figuring out what you want to run in advance, but instead basing your configurations that you choose on what has historically performed well. And the main systems challenge that arises from that is now you don't know in advance of starting your hyperparameter search experiment exactly what configurations you want to run. So now you have to build out some sort of logic, for instance, in the form of a scheduler that is able to, schedule different jobs running with different configurations on a machine, as well as accept back input to say, okay, well, how well does this configuration perform, so that it can go back and figure out what would be the next best thing to actually run. And so after you introduce that kind of logic, now what you have is you have something that can figure out what configurations you want on the fly and schedule out that work. So what you also might want is essentially if you were running, something like this manually, then you can imagine if you saw an experiment was flatlining at 4% accuracy for the last 4 hours, you would hopefully be able to kill it and get that resource back so you could run the next configuration. So that's what you would do if you were doing this manually. But when you're doing this at scale, then you need infrastructure to actually do that stuff for you. And so in a scheduler that's, for instance, running something like Hyperband that uses early stopping, what you need to now build into the scheduler is the ability to sync at a point and stop all your experiments on all your machines, figure out which experiments you actually want to continue, and then restart those experiments in some subset. So what that really requires is essentially for a given experiment to save your checkpoint, save your model weights, save where you are in the data set, any random Cs that you used, to the point where now you can just restart this experiment whenever you want. And now once you've built in, this ability to essentially run early stopping, you can also then build into your scheduler what you need to take the final step and run all this stuff asynchronously, like ASHA does in their algorithm. And so by running asynchronously, now you get a lot more resource efficiency. And ultimately what they show with the ASHA algorithm is, of course, you can run 3x faster than Vizier, which was, it still is, I think, the best thing that Google runs for hyperparameter search internally, or for optimization, I should say. Okay, so at this point, we have distributed training, we have bookkeeping, experiment tracking, we have early stopping, so that's like pausing and restarting again. We have a scheduler scheduling out work. And now we can essentially run large hyperparameter searches at scale. And the most common way people do this is they use the cloud. And that's because, with cloud, you can use whatever resources you want, you get whatever image you want, you can have whatever hardware that you want. But the main downside, of course, is that running on the cloud is very expensive. So I think with a Pre-3 2x large, which I think is just one GPU, that is $3 an hour. And so if you want to run an experiment where every training run lasts like 8 hours and you run 100 experiments, then that turns out to be a $12,000 experiment. So what will typically happen if you tell your PhD advisor that you want to spend $12,000 on an experiment is that they will say that you should run spot instances where, or preemptible instances on GCP, where essentially, yes, now there is, it's like 90% cheaper, but they can essentially take away this machine anytime they want. So if you're running on preemptible instances without extra infrastructure support, you can expect essentially losing data all the time, or losing saved progress all the time when an experiment or when a machine goes down. In addition, you would also have to track exactly what experiments went down so you actually could restart it. And if your machines are going down fast enough, then you might not ever even be able to finish your experiment. You might always just be restarting things. And so if we want to run on on-demand instances, that can save us essentially, like 90% cost on every machine, but we also now have to build into the scheduler the ability to have fault tolerance when machines go down. Because now it's not something that, would happen all the time, or sorry, it would not happen rarely, but it's something that we could expect to happen essentially all the time. So with all that infrastructure support and I guess some of these things that I haven't talked about as well, what you essentially get is orders and orders of magnitude of more efficient HP search. So if you imagine running on 4 machines, you get 4x performance improvement for distributed training, maybe 3x improvement over something like Vizier with ASHA, maybe 10x cost savings by using something like preemptible instances, which back of the envelope maybe gives you 100x savings. And this is the kind of savings that is essentially reported in machine learning literature, but with the asterisk that it requires all that infrastructure work that I talked about earlier. Cool. Yeah, so I just also wanted to briefly touch on some things that I've learned about experiment tracking, especially at Determined. I will say that I didn't do this well. Sorry, was there a question?
Angela, yes, I had a question about spot instances stuff. Sorry to interrupt. Is that available today on Determined? Can we kind of go and try that, or is that like an enterprise-only service? Because I know the Determined system is open source, right?
Yes, yes. So that's available in the open source version, so you can start using that today.
I see. So the scheduler that orchestrates the buying of the spot instance and then the fault tolerance is also part of that.
So I think you can configure if you want to use spot instances just manually on your own, but what Determined will make, or what Determined will take care of, is actually doing the fault tolerance and the checkpointing and the scheduling on those spot instances.
I see. So what does the user give? Do they give like a budget or something like that?
So the user provides, I think there's 2 ways to do it. So I think the user can both provide essentially the machines that are available. Mm-hmm. That they requested from AWS.
I see.
But also there is an auto scaling approach that you can configure for the Determined master as well. which would essentially scale based on the amount of work that you needed to do.
I see. Okay, sounds good. Thank you. Let's continue. Any other
Cool.
questions from the students at this point? I don't see any on the chat so far, but yeah, let's continue, Angela, and then we may take more questions at the end.
Oh, sounds good. Yeah, I think this ability to run on spot instances would have been one of the very useful things to have in grad school.
Oh yeah, definitely.
Cool. Okay, so just a little bit on experiment tracking and reproducibility. So I already talked about how I had basically a horrible way of doing this in grad school. But at Determined, I would say that two main things I think make a big difference here. One is running containerized training. So the typical thing that I would do, probably most people do, is rely on virtual environments to essentially say, whatever Python packages you needed to produce a result. But if you've ever tried to reproduce a result that's like shared in some code base or from a paper, what you find is that the virtual env typically isn't enough to actually get it running. Also, once you start moving into production, this becomes not what you need, because essentially you're going to be wanting to run on a lot of different environments. There's a lot of different types of hardware that you have access to, but also your actual production environment itself will be likely very different. And so what's been a much more scalable approach is to run your training in a container, like using Docker. So the other thing that I think makes a big difference is instead of relying on something like a file system to store all your data, I think what's really useful is having a way to structure this data in a way that's organized, but also in a way that you can actually query programmatically. And so for something like the experiment results, what you'd want is to actually have those experiments results persisted in a database somewhere. And what this allows is, number one, now this data is structured. You can expose APIs that allows you to deal with this stuff programmatically. This essentially allows Determined or other systems providers to provide those HP search visualizations that I talked about by automatically querying the results of your hyperparameter search, or to provide the web UI interface that allows us to show you the results in real time, as well as share them with different team members. It really makes a big difference here. It also makes a big difference with logging, because when you're running, if you're doing engineering for ML, typically you're dealing with logs at many different levels of your system, many different levels of your workflow, I should say. So all the way down to like CUDA errors from your accelerators, as well as PyTorch and TensorFlow errors. So what you really want is a way that, to structure and organize your log so that you can access whatever level you want, that you can figure out what level to actually zone into, and that you can query for particular things. And again, in that case, something like log manager or database is really useful. And this is not to say that if you're a machine learning engineer or like a grad student that you should be rolling all this stuff out, but that this is the kind of infrastructure that you should be looking for early on when you're starting a machine learning project to add into your workflow, because it just makes a difference moving forward. Okay, and finally, I just wanted to talk a little bit about infrastructure management and cluster management, especially when we're working with deep learning workflows. So, the main problem that we're trying to solve with infrastructure management is that, you have a set of GPUs in your cluster, maybe like 40 GPUs, and you have maybe 7 team members that's all trying to share these GPUs. And so what you want is, among other things, a cluster scheduler, where users can submit jobs to the cluster. And then the cluster will determine, for this particular job, where and when should I schedule it. And there's a lot of traditional schedulers that do this, things like Yarn or Borg and Google. But they really differ from what we think is useful for cluster management, because again, they're running a different set of workloads. So in traditional schedulers, typically what you see is that a one-time placement works. So you can look at, what kind of resources this job wants, figure out where and when it runs, and then leave it there for its entire life cycle. And you're making this decision based on, providing high resource utilization in your cluster, as well as fairness across your team members. And to figure out if you're doing that, it basically suffices to do systems level profiling, like figuring out what is your GPU utilization, or to make sure that jobs aren't getting starved. But what really changes in a deep learning workload environment is that, for one, your jobs are a lot bigger. So instead of running for like minutes or hours, it could be running for days or weeks. We also have the ability to take advantage of the fact that a deep learning job, or any really machine learning job, has a very specific cadence to it. So you're always running, batches within epochs, for instance. And also what we find is that, given these two things, the actual pattern of working with deep learning jobs is much more iterative. So what you do is you run a job or a training job, you likely don't actually let it complete, you figure out, what you need to figure out from it, you stop it, and you start a new one. So in OSDI 2018, people proposed, a different cluster scheduler for these workloads called Candiva. And really the difference is that it's a very introspective and iterative workload that they offer, or support that they offer rather. So now when they're making scheduling decisions, the scheduling decision in itself is essentially continuous. So you can essentially have dynamic scheduling where you can either, start or stop machines, or start or stop experiments. You can migrate experiments to different hardware. You can scale out experiments to many machines or scale down to fewer machines. And to figure out, what you actually want to do here from a scheduling perspective, you also get the ability to introspect on how a job is doing. So now with a long run training job that takes, for instance, weeks, then you no longer really suffice to have one metric showing, how this application is doing. What you really want to measure is batch level work. So what we found in industry is that this is pretty much spot on. These are the kinds of things that we need in production. And in addition, we also need, the additional scheduling approaches that we essentially talked about earlier, to coordinate distributed training, to coordinate fault tolerance, to coordinate something like ASHA for hyperparameter search. Okay, so any questions up until now? Actually, we're kind of close to the end too, so I can kind of just round this out. But essentially, we've talked about a lot of the infrastructure challenges that I have had, that we see our customers having. And really this is meant to be, first and foremost, a testament to how much interesting systems work there really is to power deep learning. But this is also, why companies like Determined AI exist. These are the kind of problems that we're setting out to solve. And it really goes back to, improving that experience for someone that's trying to do machine learning. Because ideally, again, what you want is that if you're running machine learning, or if you're a machine learning engineer or data scientist, to really live in places like PyTorch and Keras and be thinking about machine learning code. And then to essentially offload any of this additional infrastructure management or software, or I guess systems work or boilerplate code to a system like Determined, but still in a way that you have the flexibility to change things about your workflow that you want. So if you're so inclined, I encourage you to try Determined. For instance, if you want to use spot instances, if you want to run hyperparameter search, or just if you want to, actually see your results in a web UI or distributed training. And if you actually do run Determined, please reach out with any questions you have. We're always on our community Slack answering questions, or let us know any feedback or any other questions or concerns that you might have. We'd love to hear from you. Okay, that is all I had. Thank you guys so much for your attention, and happy to take any questions.
Great, thank you, Angela, for the nice overview of the systems issues and your work. Let's give Angela a round of applause. We're gonna do this virtually in the Zoom icon. That's how we do it these days.
Understood.
Okay, questions for Angela from the audience. Feel free to raise your hand, unmute yourself. No, clear this all. Um, let's see. I don't see a question. Then I can start off the questions. So Angela, couple of things regarding the infrastructure management. One, I was surprised that CMU doesn't have a cluster. Does it not have a cluster that grad students can share?
Yeah, so we have two clusters that I know about at least, and almost none of them were ever enough for my purposes or anyone's purposes. I think that people can always use more GPUs.
I see.
And so it was always a matter of getting more.
Interesting. Here at UC San Diego, we are fortunate to have the San Diego Supercomputer Center and Cal IT2, and we've been running this for decades. And so we have a lot of in-house expertise on running clusters. And fortunately, our grad students have not suffered so much because we have like the Chase CI cluster, we have the Comet supercomputer and stuff. That said, when I spoke with ML faculty before I started working in this space, they said exactly what you said, which is I asked one student to run one experiment on each different GPU, and then they report together what the results are. And they call this graduate student descent, GSD. And it seems to have been the state of the art like 4 years ago, manually partitioning your whole papers, workloads. Now I think, thankfully, things are starting to look better. So question on the infrastructure management part. So if an organization has an in-house cluster that has infrastructure, how would determined work with that? Like if, say, a university has a cluster that is shared by the entire department. Like here, for example, we have a 100 GPU cluster, and that is shared by our faculty and students, including those who teach deep learning classes, those who do deep learning research. How would determine play with that environment?
Yeah, so I think it depends on, if the majority of people are running deep learning workflows or not. So if they are, then the best thing would be to just run determined as is as the cluster scheduler. If they're not, then the options are to partition a set of the machines for determined to run, particularly for deep learning workloads.
I see.
In addition, we have Kubernetes support, but I think a lot of academic clusters actually aren't using Kubernetes.
They're using.
Yep. Okay, cool. Yeah, so we also have Kubernetes support, so we can run on top of Kubernetes as well.
So can it be co-located? Can it be a concurrent cluster on the same machines where determined runs and something else also runs?
Yes, with Kubernetes, yes.
Got it. Okay, cool. The next question I had was regarding the experiment tracking and stuff. It's sad that in the deep learning and the machine learning research world, like the NeurIPS ICML community, I don't know if you see the latest surveys, many people do very ad hoc tuning, and they don't even keep track of hyperparameters that they ran, and there's a reproducibility mess. So it's good that we have more tooling support to automate some of that logging and provenance management. Last week, we had Mate visit us to give a talk about MLflow. And MLflow does a lot of the same things, but for more general machine learning workloads for kind of various kinds of ML tools. What is your take on determined's capabilities in this space against, say, what MLflow offers? Like it can also work with PyTorch and other ML tools if you want. Is there something specific to deep learning that we need to track more?
Yeah, I think that MLflow, if I remember correctly, a lot of it is about tracking metrics and having a model and tracking model artifacts with a registry. Am I right in that? And I think that they do a really good job with that. So with determine, we really focus on having an integrated solution where we have essentially the way of doing experiment tracking hooked up with hyperparameter search, for instance. So we know for a hyperparameter search exactly what we want to track, exactly what we need to do a hyperparameter visualization, that kind of thing. We actually converge on pretty similar things. At the end of the day, you just want batch level metrics, you want your final metric of interest. We also have a model registry, for instance. So all those things for the most part are things that I think MLflow has. But I would say where the solution differs is when we want to integrate with other parts of our approach.
Got it. So if they're running these scheduled hyperparameter search with MLflow, they would have to do a lot more setup and hooking the infrastructure, whereas with yours, it's out of the box.
Yeah, exactly. Because there are a lot of point solutions out there for all of these tasks that I talked about. I think that in my experience, the most difficult part about that was just getting the inputs and outputs set up. So if you are running hyperparameter search with something like Raytune or Optune or whatever, you need to figure out how that integrates them with MLflow, and then how maybe that integrates with weights and biases if you want to then showcase those results in UI and share the results.
Okay. Okay, so one of the things we did, so we've been running this Cerebro system. I don't know if you're familiar with that. It came out this year, where we also built this model selection system for deep learning. It's a hybrid of data parallelism and task parallelism. So the basic idea that you talked about, right? So you have shards of data, you parallelize one model, and then you have task parallelism where you run independent models on independent workers with the whole data set on each worker. And our setting, the restriction was we could not copy the whole data set to each worker. It's a scalability bottleneck. And so we just operated on sharded data, but then start each model on each shard and then hop across the workers after you see that shard. So it keeps rotating across the cluster. We call this model hyperparallelism. And it seems to work very well for the workloads that we have with our constraints. One of the things we realized was the data ETL and the input-output orchestration stuff. We don't want to rebuild that part. So we integrated with Spark. And so now it kind of works out standalone or works with Spark. And then we realized that Spark has also kind of tried to integrate Horowod into its framework. It now has a more general scheduler. We tried that too. Horowod seems to have gotten more adoption and traction.
Yeah.
You see that continuing. So PyTorch, for example, recently also released DDP, the distributed data parallel, where they took the ring allreduce like Horowod, and they presented it again this year at a database conference. So Cerebro was at VLDB, and then DDP was at, I think, also at VLDB or Sigma, I forget. This was this year. And there in the PyTorch DDP, they talk about communication computation interleaving. So rather than the regular Horowod where you have the models, the state being exchanged and then the worker sitting idle, here they kind of stage it out so that the communication and computation are pipelined. And they showed that PyTorch DDP was better than the regular ring allreduce. It provided higher speed up. However, setting it up and getting it working is still a pain. And it seems like different forks of Horowod or different derivatives of Horowod coming up with different optimizations might lead to more confusion. What's your take on this? Do you think there is a unified variant of Horowod where all these optimizations can be integrated, like Spark Horowod, PyTorch GDP, the determined Horowod, and so on?
Yeah, I mean, yeah, I do feel like abstracting the communication patterns of distributed training and even setting up the machines, I think like should be abstracted from the user at this point. Like I can imagine that there continues to be, you know, new algorithms to be running this, but it would be nice as an ML engineer to not have to actually think about what communication algorithm is happening. Like maybe you could switch it out as a config, but other than that, I think you just want to be able to get set up and running. And like I said, I think that is really what made Horowod so popular, is really just like the easier user experience. And I would say that, I mean, I should have said this, I would say that right now still it's like the most popular way of running different, you know, running a script on multiple machines. And it's actually what Determined uses under the hood. I don't actually know if I mentioned that. We run Horowod under the hood. But you know, what would be really nice is that if we could also switch you out to DDP without you even knowing it, or just making it a config change. And I think that's the thing that would be ideal.
I see. So then the general direction is to have flexibility for different runtime backends where the user doesn't need to change much in their code. They just specify a config. That makes sense. I see a hand raised. Noah, go for it.
Yeah, thanks. Angela, great talk. I'm just curious, for the enterprise version of Determined AI, which like types of organizations and which scales do you commonly see who are asking about that service?
Yeah, I would say that actually it's a pretty range of scales now that I think about it. Really, I think like the 4 things that I talked about today, you actually hit that at all scales of training, except for maybe GPU infrastructure management. But all of our customers, if you're running on like a startup, or if you're running a startup and you have a team of engineers and you need that. So I would say we run like all scales. I would say that the thing that maybe ties them all together is just how serious of deep learning they're doing. So if deep learning is something that, you know, where you really care about accuracy, or your machine learning engineers are spending a lot of time trying to get this stuff to work, that's when, you know, customers get really excited about something like Determined. And it's not really a function, I guess, of like how, you know, how big their training jobs are or how big their team is. It's mostly a function of, you know, if deep learning is pretty critical for them.
Okay, so basically all scales, but really to your point, bonded together by how critical is that to your main business line or operations?
Yeah, exactly.
Okay, thank you.
Okay, I see another hand from Tara. Go for it.
Hi, Angela. Thank you for your talk. I was wondering if there have been any user studies done on like people estimating how much time they've been able to save using determined AI.
Yeah, I would say that, so I don't actually know the numbers off the top of my head, but to go back to the earlier question a little bit, I would say that that's the thing that our customers are most excited about is the time saved but from their ML engineering team, even more than like getting that efficiency boost or getting that accuracy boost from hyperparameter search. That's been the most, that's been the biggest drawing point. Just anecdotally, I would say that, that experience that I went through of setting up the machines and running D-train, running hyperparameter search, all that stuff is condensed to maybe like essentially getting up and running maybe within like an hour or something with actually a training platform like Determined.
Okay, thank you.
Okay, more questions from the audience? I have a couple more questions. Oh wait, Supun has a question. Go for it, Supun.
Hi, Angela. Thank you for the great talk. I think it's a very interesting and important system. I have a question regarding scheduling. So you said basically a group of people can share the resources using this platform. I'm curious getting to know about your thoughts on how you implement, for example, fair share scheduling, and what particular metrics do you use? Do you support like priority or something like that, or like how you basically quantify the fairness in this setting of deep learning model training? Because in HPC world, usually it's the time allocated for the job, but when you take training of a deep learning model, you have to take into account like the data size, or whether it's the epoch convergence or like the amount of GPUs. So what are your thoughts on that?
Got you. I wish I had a better answer to this question for you, because I actually think it's very interesting as well. At some point, I also worked on fair schedulers in research, and that was also always the interesting question, like, what is fairness in this world? I actually don't know off the top of my head what our fairness metric is for our fairness scheduler, but we are introducing a priority scheduler that's in the pipeline as well. But I will get back to you. I will get back to you.
Thank you.
Okay. More questions from the students, from the audience? Okay, I have a couple of questions regarding the hyperparameter stuff. So there's this survey that came out recently from Neurups and Eichler authors, and I think half of them said one-third of them said they did manual tuning, half of them said they did grid search, and then like very, very, very small percent said they did more sophisticated AutoML procedures. Why is that? And this is this year or last year. So this is like this, and these are the people who are at the cutting edge of ML, and they still don't like any of these sophisticated AutoML procedures. They still prefer specifying the grid and then constructing grids and running it. My intuition is it gives more control and transparency to them versus having the machine control the hyperparameters for them. What's your take on that, both as your research hat and your industry hat that you've seen from customers?
Yeah, I mean, like, it's actually a very interesting question that, well, actually, if we go back to that like blog post, my co-author of that blog post, who also works at Determined AI, actually is one of the inventors of Hyperband and ASHA, asked this exact question in a blog post that he wrote, which is like literally called "Why Do People Not Use Advanced Hyperparameter Tuning?" And the answer that he gave, which I trust him on, is that it just is a lot of infrastructure to set up. So in that blog post, he runs through, a lot of this infrastructure stuff that I talked about, but the actual like table stakes of getting something like Hyperband to run, you need the ability to do early stopping, which means like pausing and restarting experiments, for instance, which if I'm just trying to run a hyperparameter search, I'm actually not going to roll out myself. So anecdotally, this is true for me too. I mean, that's why I did grid search. If I could have something more sophisticated just out of the box, I would have. Like I was using something like Vizier, for instance, right? And so like if Vizier had like a software, system backing to say that, oh, you can also run ASHA, I would run ASHA to make my hyperparameter search go faster. But it just requires so much additional infrastructure support.
I see. Interesting. My interactions with the practitioners seems to be they just like the transparency of grid search more. It's just they know exactly what is run and what is not run and how much it's run. Regarding the infrastructure support, there are tools that are coming out that offer more advanced AutoML procedure out of the box, right? Like Spark has hyperopt now, Dask has hyperband and hyperopt as well. Do you think that that issue will get mitigated over time and people will start using these sorts of algorithms more if that infrastructure issue goes away?
I do think the infrastructure issue is getting solved. It just hasn't been, fully adopted by everyone. But I actually do think the software is out there. Like, actually, like you can just run ASHA with determine, out of the box, for instance. And I think most of our customers do default to something like that. But yeah, I think it's mostly a matter of adoption right now that, but the actual software is offered.
Got it. Okay. Okay. More questions from the audience. I still have more questions, but I want to give the audience a chance. Supun, go again.
Yeah, so this question is basically about, so as I understood, Determine is basically focused on model building. But before that, people have to do like data preparation, and after that, people have to do deployment and monitoring. So how well and how does Determine integrate with other existing components in this space? For example, whether does it integrates well with like ETL systems like Spark, or like and other deployment systems for inference, like so for example TVM or so on. And the second question that I have is what type of data does most people use in your customers use? For example, is it mostly unstructured data like text-based models or like images, or like is it data mix of both like traditional, relational, and like also unstructured formats?
Yeah, so I guess first on the first question of like our integrations with other parts of the pipeline. Yeah, so we're really focused on training. On the data loading side, I mean, I think the data loading side is still like a mess right now. Like people just come in with data of all different types of forms. And, data is big, or it's hosted in different places. Like you can't just like bring it in with a tar file and put it like on your image. And so I would say what we're seeing is that it's still, not converged on a particular solution. That being said, like we have integrations for, some of these workflows. Like I think we have an integration with Pachyderm. We have, our own techniques of, actually, so taking, a data set that's on a bucket and streaming it to your training interface, streaming it in a way that, it's reproducible, sharding it in a way that it's reproducible. But I would say that there's still a lot of work to be done with integrating with more ways that people are getting their data into here. Just doesn't seem to be very standardized yet, as far as I can tell. And if you guys have a preferred method of pre-processing your data, that's also really good information. On the second question of what do these data sets look like? Yeah, so this is something that I learned actually with my time at Determined, is that these production data sets are essentially just like lots of files of unstructured data, as far as I can tell, from a lot of different sources with different formats that really like need to be parsed and cleaned in a way that it's, a reasonable data set to be training on. And that's just very different than what I'm used to in academia, where we're working mostly with just common data sets. And so that's something that I thought was interesting coming into production, just how unstructured and ad hoc a lot of these data sets are put together.
Okay. So, Pun, did you have a follow-up?
No, thank you for the answer.
So what sort of, following up on that, what sort of applications are you seeing people using this for? Like, are we talking like fraud detection? Are we talking like, what sort of application? Video monitoring? Do you have an idea from your customers? What sort of applications people are using this for?
Yeah, so with customers, like, yeah, customers again are very different than like the open source community. And in that, like, I think one of the things that they focus on is interpretability,
Mhm.
and which deep learning is not great for. And so for things that are like very key in a pipeline or that needs explainability, like for instance, something like fraud detection, I think deep learning is not really an option for them. So what we actually see is, I think mostly like computer vision applications, but that are used more for research or for exploratory things, as opposed to, you know, like user facing applitions, if that makes sense. So both in terms of like autonomous vehicles or medical applications, you know, like all the industries that you hear of, but I would just say things that aren't user facing.
I see. Okay. I vaguely remember from chatting with Amit that you're also interacting with a genomics company or a genetics company for some sequence processing. So what type of data set is that? Is that textual? Is that sequence data?
I believe that's images. I think that's images of cells. I could be actually totally wrong about that. It's one of the applications that kind of goes over my head. But I believe
Images. I see. I see. I was wondering if those are like sequence data. Okay.
I know. I think it's detection of images.
Got it. Got it. Okay. More questions from the audience? This is very fun discussion. Thank you for sticking on. I mean, we have another 5 minutes. Couple other questions in the cloud versus prem, right? This is a perennial debate. Many people have in-house clusters, but they don't want to maintain and operate and manage them. The DevOps headache is too much. So a lot of enterprises do want to go to private cloud or hybrid cloud or even just public cloud. What is the takeaway that you're getting from speaking to your customers? Is there heterogeneity that is going to stay? Some people want on-prem, some people want in the cloud, some people want both, or is everything moving to the cloud?
Yeah. I mean, I think at least in my view, I think the typical pattern is that there's a hybrid approach, but most people would like to use their on-premise cluster more if possible, just to save money.
I see.
So that's one of the things that, you know, when we're running determine, people have questions about, which is like, how much are we running on the cloud? How much are we running on premise? And can we move more onto on-premise?
So they actually invest in GPUs for on-prem clusters.
That is what we've seen for our customers, because again, our customers are people that do have deep learning like pretty integrated into their workflow. And so they have like spent the effort to roll out some of their own infrastructure and even their own software as well. But yeah, I think that could change as it becomes like easier for startups to actually just like spin up machine learning, even if it's not, you know, like hypercritical, and maybe that would all happen in the cloud. But we are seeing that most people have an on-premise cluster, I would say.
Fascinating. I mean, the evolution of cloud architecture itself is moving towards hyper efficient kind of resource disaggregation. You want to be able to rent stuff at the level of milliseconds now in the serverless environments and so on. So resource disaggregation, like what they call the next generation cloud, will enable a lot more resource efficiency comparable to the Spot instances, but now for everybody, not just for Spot instances. That's the vision, or that's the goal I'm hearing from many of these people who are doing this cloud infrastructure research. In that space, how do these systems like Harvard work? Because they are so coupling, they couple these workers so much. Do you think if you have an elastic infrastructure where workers come and go as they please, can things like Harvard still scale in those environments?
Yeah, I mean, I would say that that's where like, not to always go back to determine, but that's like the layer that I think determine really helps with, which is like having that more like continuous like scheduling placement of something like Horovod. Because yeah, you're right. Like if you're just running Horovod, it's just going to be a long running process on a single machine. But what ideally you would have is to be able to move that job if you needed to pause it, to restart it, and to do that all quickly. And so I think that's what like another layer of logic actually provides you, just that flexibility for scheduling. That being said, like I wonder if you know, some of this microservice stuff is very applicable to machine learning, just because like in and of itself, the machine learning jobs are so long running, and the teardown and setup is still pretty high. Like even with all the extra like logic that determine provides you, you still need to be like checkpointing pretty often and loading in a checkpoint. So it's not, you know, free to pause and restart these jobs if you want to move it. But it's interesting though.
Yep. You have to read and write from S3 every time.
Exactly. Yeah.
That's not
Not the most lightweight thing.
Yeah, that's true. So looking longer term, SageMaker and Azure ML are very active in this space too, right? SageMaker has been trying to roll out end-to-end stuff, AutoGluon and AutoML stuff, and notebook infrastructure and all of that. Do you think the cloud vendors are going to consolidate in this space on creating more deep learning infrastructure that is cloud native going forward? Or are they going to be perennially they have a perennial Achilles heel in that the previous point that you mentioned, a lot of enterprises still like on-prem, especially for deep learning or a hybrid model. Is that going to be an Achilles heel for the cloud vendors?
Yeah. I mean, I would say just selfishly as someone that runs ML, I think it's great if the big cloud companies actually provided their software. Like in a way, like all the stuff that we're talking about building out is stuff that, we had at Google Brain internally for a very long time, but it's just not available open source. And, it's available in something like SageMaker through like a very small subset in their API and stuff, but it's not flexible. So I think it would actually be great if we had more access to their internal infrastructure and deep learning management workflows. But that being said, as of right now, I would just say that it's just not exposed to the user yet. Like something like SageMaker, I think does work pretty well if you just want to run basic object detection or basic, image detection or NLP applications. And so maybe that does work for that new emerging startup in the future that we were talking about that just wants to try out machine learning really quickly on the cloud.
Okay.
But I think as you start to do more serious deep learning, you start to really want that flexibility. I mean, that's actually what we've seen at Determine too. We provide all of this infrastructure support, but it continues to be very important for our customers and users to have insight into what they're running and being able to change it.
Right.
But yeah.
Okay, sounds good. Last question from the audience, anyone? If not, one last question for you, Angela, about your own experience. It's great to see more companies building support for enterprise users in this modern AI space, because all the big tech companies are hogging a huge amount of talent. They have been hiring and gobbling up deep learning specialists and engineers for the last 5 years. Google, Facebook, Amazon, Microsoft, Apple, all these big companies. Although I'm hearing now there's a hiring freeze for deep learning researchers at some of these companies. In any case, there is a vast world out there that is struggling to adopt modern AI in the enterprise world, in the sciences and the academics and so on. So it's great to see more companies and more folks like you joining companies that want to build out these sorts of software infrastructure for what I call the democratization of modern AI. So what made you choose this career track rather than say go to the fair and the deep minds of the world? Why do you want to build these sorts of, what inspired you to build this sort of enterprise-oriented software? And two, what tips do you have for students who want to go into career in ML engineering?
Oh, interesting. Yeah, I mean, I guess I would say for me, it was more of a choice. I knew that I wanted to do startups. So that wasn't anything about the field or anything in particular. Okay. Yeah, but how I chose Determine was essentially all the stuff that you had talked about. It just seemed like there's a big vacuum for this. I went to Google Brain, I had all of the infrastructure available to me. Life was actually very, very peachy. And then when I was leaving, I was like, well, I don't understand. I'm going to go back to research, have to roll out all this own and still have to have results. This is pretty intense. And so I think I just personally felt that need of having, like you said, more of a democratized AI platform. And also just in general, because I'd followed startup space, I was surprised that, for the last 5 years when I was in grad school, that you don't really see as much of proliferation of startup that use ML or robotics or whatever cropping up all over the place. And I think, like you said, it's just a testament to that the infrastructure is just not there yet.
Right.
So I think ML systems is really, really interesting. And I do think that, mixed with, I think startups are interesting and I think everyone should consider it, that, that's kind of what drove me to this place here. Yeah, as far as advice goes, I would just say that like work with people you like. It's kind of orthogonal, but it was advice that I had gotten and I kind of followed in like a very vast search, and it landed me in a place that I enjoyed. So maybe I'll share that as well.
Okay, sounds good.
Yeah.
Thank you, appreciate that. With that, we are out of time. Any last question from the audience? If not, let's give Angela another round of applause. Thank you for sticking around and answering our questions, Angela. It was a pleasure to have you.
Yeah,
And
thank you
good
so much
luck for all the stuff that you're doing at Determined.
Appreciate it. Thank you so much for having me. This was really fun.
Okay, take care and stay safe. Say hi to the others there.
All right, will do. Bye.
Bye.